Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We'll go ahead and get started. I want to welcome Mari Ostendorf to give a talk here today. I won't go through the whole litany of her background. I do want to say that Mari is very close to us here because she is close geographically, just across the lake, and it's really nice to have her here to give a talk today. She has a PhD in electrical engineering and has been at UW actually since '99. And does a lot of work on speech processing. I know a number of projects that you've worked on with a number of folks over at UW. And what she says here is interests are in dynamic and linguistically informed speech and language processing, which of course is of interest to a number of folks here. Mari and I actually remember, I've known Mari for about 10 years, and I remember distinctly the exact moment I first met her. It happened to be in an interview across the table at the faculty club, so it was a grueling day. Fortunately, I had the opportunity to work with Mari intermittently over the next couple of years in the development of the Ling program at UW, which was a distinct pleasure. So without belaboring it any further, Mari Ostendorf, Finding Information in Disfluencies.
Okay, thank you. All right. So I'm going to talk about how we really talk. So I'm assuming, I know some of you actually know a fair amount about disfluencies, but I'm assuming that some of you don't, so I'll have a little bit of an intro here. So this is a transcript from the switchboard corpus, which is conversational speech. And what I did here is everything that is a disfluency, I have put in bold and crossed out. So classic, and then filled pauses, and that's filled pauses. Those are in purple to the extent they look like purple here. So this is just illustrating different types of disfluencies and the fact that they are fairly frequent. The other thing that I want to, so I'm an engineer, so I actually have practical reasons for thinking about disfluencies, even though I'll give you a lot of studies that aren't so engineering oriented in terms of what we're looking at. So if you think about what computers would hear if they were perfect, it's everything that comes out of somebody's mouth. That's what the recognizer, there's an acoustic signal there, so the recognizer will deal with it. The dots are there to indicate that we've got some pauses in there. And then if you look at what people hear, people actually filter these things out. So many of those things, not all, but many of those things, depending on how they're said, the listener won't even notice. And if you ask them to transcribe the speech, they will miss quite a lot of it. So that is the challenge. If we want our computers to be like humans, we have to figure out what to not pay attention to. Okay, but now I'll come back to that. So the other thing I want to point out, a lot of people thought, had this idea that switchboard is it's just really messy data. It's not real life because it's not really practical because these people have no stakes in the conversation. They're getting paid some minimal amount to talk to a stranger for 5 minutes. Well, okay, here's a nice example. This is Supreme Court oral argument. They are, in fact, more disfluent than the switchboard corpus. So, disfluencies are real life. And if you think about when are we disfluent, well, one of the reasons we're disfluent is when we have high cognitive load or emotional situations. The Supreme Court is definitely a high cognitive load situation. Okay. All right. And then I wanted to point out here, this will be relevant to the particular approach that we're taking. This is one sentence. Okay. So from the point of view of how it's transcribed, and one of the things you see in the Supreme Court oral arguments, people, particular lawyers, don't want to give up the floor. So they make their sentences, they make it hard to be interrupted. And so this is going to pose problems for language processing. All right, so disfluencies are common. Multiple studies have found disfluencies rates of 6% or more in human-human speech. So that's relatively high. You can't avoid having to deal with it. People have some control over their disfluency rate, but pretty much everyone is disfluent. So some people are more disfluent than others, but pretty much everyone is disfluent. People aren't usually conscious of the disfluencies, but they do appear to use them both as speakers and listeners, and as you are using with your robot. Okay, so I like to argue, traditionally in language processing, people have been thinking about disfluencies as noise. And I would like to point out that they are also information. So they're noise, they're both, okay? They're noise because if you actually transcribed exactly what somebody said, it's hard to read, okay? So it degrades readability. The word fragments are difficult to handle in recognition. They mess up the recognizer, and the grammatical interruptions mess up the parser. If you translate them, everybody gets confused because the prosodic cues that tell the listener to ignore this aren't there. So for all those reasons, disfluencies are noise. On the other hand, listeners use those disfluencies to understand the corrections, the attention grabbers, the strategy changers. They use, how they use particular filled pauses is sending a message about turn taking. They indicate speaker confidence, and the disfluency rate reflects cognitive load and anxiety. So it's interesting from a human-computer interaction perspective to look at them. So detecting disfluencies impacts, from a practical perspective, getting the intended word sequence, interpreting the speaker cognitive state, and understanding the social context. So, and as I will actually show some, one little study that we hope to build on, it actually is going to tell us about relations between people, power relations. Okay, so this has implications for spoken language technology, human-computer interaction, particularly multi-party, because you're going to have more disfluencies that way, and spoken document processing, as well as medical diagnostics. Okay, so that's the introduction. Here's what I'm going to try to talk about. So what can we learn from disfluencies? What about the speaker mental state or the social context? How do we detect them? There's not very much annotated data for disfluencies, so how can I detect them for other types of corpora? I'm going to look at detecting, look at work on several corpora. I will call it speech in the wild, borrowing from Liz Schreiberg. And in this data, we're going to look at different communicative contexts, so high stakes, low stakes, stuff like that. And looking at automatic detection algorithms. And a side effect of this, I think we're learning about improving spoken language processing for different genres. Okay, so I'm going to start out just going through some basics of disfluencies and telling you a little bit about my data, how we do automatic detection, and some studies we did with the different corpora analyzing this data, and finally conclude. So here's some basics. So people have looked at disfluencies since the 80s at least. So there's been psycholinguistic studies that basically describe a lot of the things we are seeing now, even in a very small amount of data. So in this particular study by Lavelle early on, they identify a bunch of different types of disfluencies. including appropriateness disfluencies. So you want to change what you say. There's more strategic. Error repairs, you make a mistake. A thing that's called covert repairs, that's a particular level. Well, I'll get into the cognitive level. So covert repairs are when you say the. So when you do repetitions, and then there's a bunch of other repairs. And this is a very small study, but you look at this, I think it's pretty cool that this sort of stuff carries over to a lot of the data that we're looking at now. And they propose that well-formed repairs have syntactic parallelism between the reparandum and the repair. So the particular model that lots of people use that builds on this, described by Liz Schreiberg, is this notion that you have three parts. The reparandum, that's the stuff I was crossing out. The interregnum, that's optional. That's things like ums and uhs and I means and stuff like that. And then the repair, that's replacing the reparandum. In a restart, the repair is not there. The interruption point is not explicitly there. There's not necessarily a clear signal of the interruption point, except for the fact that you've got a prosodic discontinuity. So here's an example of the very first, in the form of the first stuff I showed you. This is that annotation of this crossed out version where I have purple for the reparandum. Here's my interregnum. So the person is saying or to indicate their rephrasing here. Of course, you can have disfluencies inside disfluencies. So that's what's happening here. And this is a repetition. So that's basically illustrated. Yes?
Why do you think that the stand they have, it was not intended? Why do you think that the phrase, the stand they have, was unintended?
So this is something that would probably be categorized as an appropriateness disfluency. So the person wants the way they command respect to replace the stand they have. So in reading the broader context of this.
Okay, you get it from the broader context, okay.
Well, actually, you can get it from listening to it, too.
Yeah, prosody, sure, but
right.
Right, in terms of text there, I don't see any reason that that's considered a disfluency.
So all of these transcriptions were this is from the switchboard, and this was all based on audio. So the transcriptions are based on audio. The way that I would get this from text alone, so ideally you want to do the automatic detection with audio, which I'm not doing right now, okay, which I'll explain. The way that I would get it is the fact that there's a repetition here. Not just yeah, okay. So anyway, this is the cleaned up version. Okay, categorizing, so there's three categories that have been used in a lot of the recent work based on this simple surface level labeling. A repetition is when the reparandum equals the repair, a restart is there no repair, and the correction is when they're not equal, all right? Earlier work by Levelt and Cutler had finer grain intention categories. And eventually, I actually think this is the really interesting stuff in terms of analyzing interactions. But at the moment, most of the work is really aimed in this, and that's where we're going to start. And in fact, most of the work is aimed only at finding the reparandum. So this is just some examples. Repetition, it's. Those are very frequent. Repairs. There's a lot of different types of repairs. So the person is getting rid of the just. We you'd, so there's strategic things. There's, so we want, in our area we want, so there are elaboration. And there's also mistakes. I don't have an example here. Well, we would be a mistake. You can also get words being wrong, lexical access mistakes. So there's a lot of different types. Restarts, this is an example, and you can have them nested. Okay, just to show here, the interregnum, it could be filled pauses. It could be things like I mean, discourse markers like well. And one of the reasons why you want to, why you want to not just throw it away, and why you want to, so mostly people have been detecting these things and throwing them away. But in fact, sometimes, not hugely often, the word that you want, my insurance, is in the referendum but not in the repair. And so you actually need to not throw that away. Question?
I was wondering, on the previous slide, I was wondering if most people have been working on the surface
Yes.
result, because, I mean, you said that, is that because the goal of the work is usually just to clean up transcripts?
Yes.
So that's all that people care about?
Yep, absolutely. And so I'm just, well, also, and it's easier, right? So one of the things that Liz Schreiber pointed out in her thesis is people, you know, there's a lot of different viewpoints on how you categorize below the surface. And the surface stuff, it's pretty non-controversial. Okay. All right. So what makes people disfluent? And I'm only going to talk about, so there are the strategic turn-taking disfluencies, but what I'm going to focus on here is cognitive load and situational stress. So cognitive load, if you have many things on it, so people talk about disfluencies on different levels. So there's the articulation disfluency, when basically when your production and your planning get out of sync. So if your production is ahead of your planning, you're out of sync. So at the articulation level, that's when you say the. When your production is ahead of your planning. At the lexical access level, sometimes you make things like review, renew, or something like that. So lexical access, things that are similar sounding or different, wrong tense or versus an. And then there's the more planning, you know, overall planning level, and that's where you make some of these appropriateness to strategic changes. So cognitive load, you have more disfluencies because you have multiple things on your mind. Situational stress, high stress will tend to, I'd say cognitive load seems to get everything. High stress, from the data I've looked at, seems to have more of the lower level disfluencies. An interesting thing is you kind of have low stress and high stress. If you have really low stress, very casual conversations with people you know, they're more disfluent. And if you have very high stress situations, high stakes, it's more disfluent, and it's kind of lower in the middle. Based on the data I've looked at, the problem, all this with the caveat, there's such vast variation in speaker disfluency rates that's the, you know, individual speaker variation is a huge effect, and you need to look at a lot of data to say anything.
Why would the low stress situation increase disfluency? Is it that you just don't care, or you're thinking about other things when you're
you're not
engaged?
using most of your brain.
You don't
Yeah,
care what you
okay.
say.
No, you know that, okay, so some of the very disfluent stuff that we've looked at, we had to totally change how we were annotating, was call home corpus, or call home, call friend, because you know the person you're talking to understands what you're going to say and you don't finish your sentence. So you can be very sloppy because the person knows you very well. It's a very grounded conversation.
Okay.
So do you get then disfluencies that don't in fact have the correction?
Right.
Okay.
Right. And you actually get the word that it finishes the sentence in the next sentence by the other person.
Yeah.
So that's very tricky data. And actually, we see this in some data that was collected at UW recently by Gina Laveau and Richard Wright in terms of this negotiation. So in negotiate about something, also if you have a shared visual world, they may say something that's in the picture of in their world, shared world that they both are looking at, but they don't actually say it. So all of those things cause disfluencies as well.
Is there any data that you've looked at that shows sort of some consistent pattern across languages?
I've only looked at English, and that's pretty hard as it is. Okay.
So you're talking about only about native English speakers here. So
No, I'm talking about the English speakers in the corpora we have. And so most of them are native, but not all.
not native, there could be some additional factors.
Right.
Because the
Right.
language may have different kind of structure there.
Right. Most of them are native, but there's no guarantee. Okay, so the interesting question is, are these factors reflected in different disfluency types? I argue yes, by the data that I've had, but clearly it needs more analysis. Okay, so I talked to you about the cognitive models already. Basically, there's the content planning, the lexical access, and articulation, and what's happening is generation or production gets out of sync of planning. So you also have these strategy changes, which I think is really important, something you see a lot in the Supreme Court data. So there's a question of whether the different types of disfluencies reflect different types of problems, content, lexical access, articulation, or different solutions to problems. So it has been argued by, I think it was Herb Clark, that it's different solutions to problems. I would say, looking at this data, is probably a bit of both. So here's again articulation, disfluencies. You see these repetitions, lexical access. Okay, here is the actual example to remove to review. And that's lexical access because you will tend to use as you're planning because that's the most common thing. You see this a lot in languages that have gender with their articles. And here, you can tell this is a Supreme Court one by a candidate by a contributor. So they're talking about two different parties and mixing up those parties. That's a lexical access. And then the content planning, it's a mix of things where you're clarifying your, yes?
How do you know that that's not by a candidate, by a contributor? How do you know that the speaker is not purposely saying something more about what he wants to say, augmenting? See, there's parallelism. How do you know it's not parallelism?
Well, in this case, they're talking about campaign contributions, and generally the candidate, they're talking about, it's a case about who can contribute and limits on contributions. And so in this particular context, it wouldn't make sense for this to be the same thing, a clarification, but you raise an excellent point that this is a very hard problem. So it's not an easy natural language problem. The other thing, though, is if you listen to it, the particular way somebody says it is different for those two things. And so that's a reason why we really need to get to the point of being able to include the audio. Okay, so anyway, I just wanted to point these out because for me, this is a reason why, these give reasons why we want to look at the endpoint and look at these more complex disfluencies, that the more complex disfluencies are telling us about the situation. So in this case, the lawyer says where we are arguing, where it is our position. So there's something strategic going on here. I don't know what it is because I don't know legal stuff. Here, they're expanding, they're emphasizing right to full right. But one of the things that you also see quite a lot, but only for lawyers and not for justices, is hedging. Okay. Okay. Distributional observations. These are some things that have been, a lot of people, a lot of work has gone on to looked at different disfluencies. One of the things that's very interesting in human-computer interactions in the old days, there's very few disfluencies. And I think that's because people are concentrating. You don't have the less formal, you don't trust your computer to understand you. Now that recognizers work better, you can look at data that's collected in the ATIS days and data that's collected now. It's much more disfluent now. So the more human-like our systems become, the more disfluencies they're going to have to encounter. Men are more disfluent than women. Disfluencies are more frequent in initial positions. The argument there is that's where your cognitive load is highest from a planning perspective. Speakers are less disfluent before a general audience than before people people are familiar with the topic. So I'm being pretty disfluent with you because I think that you know sort of what I'm talking about. If I was to give this in front of general audience, non-tech people, I would be less disfluent.
What data supports that men are more disfluent than women?
Tons of studies. And it's also consistent with men stutter more than women.
With relation to the first point, do you know if we're less disfluent when we speak to like children or babies or some other thing that we think we'll have a harder time understanding this?
Based on the first point, I would say yes, but I'm not aware of the studies.
Yes, so Mario, all the things you're talking about in terms of familiarity with the audience, actually there was a big theory in the 90s about hypo theory.
Right.
How does that fit into that pre-planning, production, that kind of asynchrony? Or the same model of cognition?
I'm sure it's related. I'd have to think about it. Okay. There is a study that says filled pause rates are less sensitive to task complexity and anxiety than other types of disfluencies. That's not consistent with our data. And again, you'll see that one of the things that we have here is huge variations among speakers. So if you're looking at a small number of speakers, you could be concluding something that's not necessary, doesn't generalize. Okay. All right, so disfluencies are prosodic interruptions. They're fundamentally prosodic. And I am going to do a horrible thing as somebody who has worked on prosody for many years of my life and not used prosody in this work. So several studies show a higher F0. So one of the ways you can tell there's a disfluency is you reset your pitch afterwards because you're resetting the prosody. There's sort of matching tonal structure because you're restarting the same thing. There's also the repair structure reflects the speaker intention to produce a predictable prosody. So there's lots of reasons why people are interested in prosody. In the data that I have, it's a little bit hard to get reliable prosodic features. So I'm not using it. You can do a lot with text, but long term, that's where it has to go. Okay. So the most prior studies have used either controlled speech. So in psycholinguistic studies, they want to figure out what's causing disfluency. So move the purple, move the yellow square types of things. Or low stakes conversation, such as switchboard. Much of the work on disfluencies has been on switchboard. Or human-computer interaction. In the old days, that has fewer disfluencies. Nowadays, that could be more interesting. But there's not a lot of annotated data, unless you guys have it. So we are trying to use multiple corpora with varied stakes to get an idea of what's going on here. So we've got, well, let me tell you about it, and to develop algorithms which generalize. So I have two telephone conversation corpora. So we have the switchboard data, which LDC has annotated. We augmented the annotation for a small amount because we're interested in different types. I have call home, which is family members. And then I have two high-stakes, goal-oriented sets of data, the US Supreme Court oral arguments. So there's more than 50 years worth of that. We've got 1 year of LDC annotated careful transcripts and a subset of that, like a smaller number of careful transcripts done by students at UW with careful disfluency, more detailed disfluency markings. And then we have financial crisis hearings. These are pretty interesting. This is we have two hearings with Blankfein, one when he was doing well and kind of a golden boy, and then later when he was on the hot seat and being blamed for doing bad things. And they are very different. And if I played you one audio clip, that would be the one to play. It's very interesting. Okay, and then we have this Ataros data that was collected at UW. It's two-person negotiations with a controlled variation of stakes. Yep.
On the telephone conversations, do you also have annotated when two people are talking at the same time?
Yep.
And is that also a source, like when somebody else butts in, does that start disfluencies on the initial speaker? I mean, do you have any data on that?
So I have not actually, I could get data on that because we do have the time for switchboard. We don't have it for call home. We could get it for, I think we have it for the Ataros data, and we don't have the timing for these guys, because so the reason I'm not using prosody is these things are so noisy, the forced alignments are garbage. So I need better recognition to do this. That's why I'm not doing prosody right now.
I would have thought that in the SCOTUS corpus that there wouldn't be any interrupt.
Oh, there is, and it causes disfluencies.
Okay, that's
yes. But it's causing disfluencies in the sense that the lawyers interrupt, or the justices interrupt the lawyers, and the lawyers start getting stressed out. Mm-hmm. That's what anecdotally I perceive from. I actually did a bit of the annotation myself because I wanted to understand it. Okay, so we're trying to vary the stakes, and yes.
Sorry, the Supreme Court arguments, these are recorded and transcribed, or are they transcribed? Are the court records transcriptions in toto of all pauses?
That's a great question, and I'm going to talk specifically about that. They are recorded. They are not high-quality recordings, hence the challenges. They have been done differently over the years. Another challenge to speech recognition. Nowadays it's MP3. Old days it's these big audio tapes. The transcriptions are not careful transcriptions. They are transcripts that some legal scholar would be interested in. And that's going to complicate the study. Okay, so I'm going too slow. I'm going to so the switchboard, we've got just a couple things about the annotation that's worth noting. The typical LDC, if you've ever worked with the LDC data, they have a nested annotation structure. We flattened that because it provides a better representation of these repetitions, and we want to explicitly model those. Okay, let's see. To get this flattened representation, we hand annotated a small amount, and then we automatically predicted the flattened representation. Because you have this structure, it's just a matter of taking these things out. The F-score is really high, so you can do that automatically really easily. And we have for switchboard, we particularly, when we do the speaker variability stuff, we have 20 speakers who called a lot. So the only way we can look at speaker variability if we have a lot from one speaker. So we can look in the Supreme Court, we can look at it in this data. Okay. Other stuff, we've hand annotated a small amount of data for everything. And that data, some of this data was used for SCOTUS training. Most of the data is only used for testing. So it's all cross-domain stuff that we're doing. Okay. So some similarities and differences, some similarities across the different corpora. Word fragments we find are most often associated with repetitions. This is counter to what has previously been reported in the literature. It's not so often associated with repairs. In the very informal stuff, it's often associated with restarts or abandoned things. Most of the disfluencies involve function words and simple 1-2 word disfluencies. Observations from prior work mostly hold, so high sentence initial, stuff like that. But the real thing that just blows you away is the large amount of inter and intra-speaker variability that's really over a continuum. Some differences, the more high stakes SCOTUS and FCIC have more of these very long strategic types of disfluencies. The relative rate of repetition is highest for SCOTUS and lowest for call home. So there are differences in the types of things we get as a function of these contexts. Need to tease things apart a little more to understand it better. The thing that really surprised me is the statistics for call home and switchboard are very different. So I think of their conversational, informal, they should be similar. No. Friends or family versus strangers seems to make a big difference, and a lot of this is the shared world effect. The other thing is I discovered that the interregnum can play an interesting role. So when lawyers are talking to justices, they can use your honor as a discourse marker to say I'm making there's a politeness thing. And all of this is based on hand annotated data. Okay, now I'm going to talk about automatic detection. So the computational model we're using is really quite straightforward. It's been used by other people. We're going to use a sequence model. We're going to, in particular, a conditional random field. It's basically like tagging. So we're going to label each word in terms of what part of the disfluency it is. Now, previously, there's been a lot of work, including stuff I've been involved in, looking at parsing models. And I think this is really a way to go. Unfortunately, as I showed you that SCOTUS sentence, our parser can't handle it yet. And so until we start doing some adaptation or find a way to do a better job parsing, then that stuff is a little bit on hold. So the features that we're using, that have been used, are word-based features or words in prosody. And as I say, prosody is actually important for detecting interruption points, but in this particular work, we're not going to use it. So that's what we're doing. Here's the disfluency detection model. We do a very simple begin, inside, outside sort of model, but we add the interruption point. So we know the end of the disfluency because the interruption point actually really matters when you've got these multiple ones in a row. And we have an other. So then the next thing we do, so this is the starting point. Then the next thing we do is repeat this for different disfluency types. And then the next thing we do is add some states for the correction. Okay? So baseline features are part of speech. These are totally standard stuff, part of speech tags, and other type indicators, filled pause, stuff like that. Discourse markers. Those are, so you look at the word and words around it. Word fragment indicator. You wouldn't necessarily have this in speech recognition, but we're using it because we're trying to understand what's going on. And pattern match features, so you're trying to say, did I have the same word, same phrase, or same part of speech sequence right in a row? Okay?
No acoustic features. No acoustic features here.
No acoustic features, because the time alignments are so bad. Okay, eventually I will get there, but right now this study is limited in that way. But it makes the experiments run faster. Okay, so the types of things we're looking at, multi-domain learning, and we've got leveraging some, we have separate models of repetitions and repairs, because the repetition model actually cuts across domain really well, and the repairs is different. So that tends to help us in certain ways, hurts us in some ways and helps us in others. We have explicit, one thing that other people have not done, we're explicitly detecting the correction, because we don't want to, we want to know about the relation between the reparandum and the repair. Not just throwing it, so it's not just about text cleanup. Punctuation as a surrogate for prosody is something we're using on the Supreme Court data, and looking at using semi-supervised learning, because there's so little data that's transcribed. So one of the things, here's a couple of the things that we did to, I'm just going to give you the final story, but just to tell you how we got better results. One, we tried adding the SCOTUS data. So the SCOTUS data to the switchboard. So switchboard is used for everything. So we tried adding the SCOTUS data. The SCOTUS data helps SCOTUS, but surprisingly, it did not help with the FCIC. So I didn't expect it to help with other things, but it didn't help with the FCIC. Better leveraging similarities. We find the common, what it did help with is coming up with words that are common words for disfluencies. So we looked at what's in switchboard, what's in SCOTUS, and we made this list of common words in disfluency, and we train a language model based on that to say, okay, if I see this sort of common pattern, it's likely to be disfluency. So there's some things that you see a lot that are, so you can get that with pattern match really easily, but certain other types of things aren't, are common, but you wouldn't necessarily get them as a pattern match. Okay, and then the last thing we added was distance-based pattern match features. So how far away is the pattern match? Because that, so certain corpora, you have longer disfluencies than others. And the pattern match, if you don't do distance, it becomes, so the farther away pattern matches are less reliable. So that's the point of that. Okay, so putting it all together, here's where we stand.
Can you back up just for a second? So the longer distance ones are occurring in what?
So if you have, so you can get in the SCOTUS corpus, we can get 5 and 6 word complete repetitions.
I see.
In switchboard, that's rare.
Okay.
Okay, they'd be 1 or 2 words.
In the more formal SCOTUS, you're seeing this kind of thing than in the less formal switchboard. Am I correct?
So basically, the idea is that if you allow the longer copies, then as they get, if you allow if you say, okay, pattern match, if I have a pattern match anywhere, fire this feature. The problem with that is that's going to overgenerate. So by having it distance matched, you can put less weight on it.
Right. No, I was just trying to get the sense of where the longer distance
things happen. So they happen in the higher stakes stuff.
Okay.
Definitely.
That was your answer.
Yeah. Okay, so these particular results are only using switchboard to recognize other things. And these are our best results, so it's with a bunch of improvements. So what you can see is obviously you do best on switchboard, but the cool thing is switchboard works not too horribly for everything. The other thing that's interesting is mostly the reason why things work well. So this is the number that everybody reports. Did I detect the referendum, no matter what it is? Okay? If you decompose that into repetitions and everything else, repetitions are very easy to detect. Okay? SCOTUS has a lot of repetitions. These guys have less repetitions. And so hence, switchboard works really well for SCOTUS. So this number is kind of hiding the fact, is going to be biased by how much the data has repetitions. Okay, the thing that's hard, if you try to detect other things, that's harder, not surprising. The thing that has not been done before is actually detecting the correction. Because if you just want to clean up, people don't care about the correction. But if you want to understand what's going on, you care about the correction. That's really hard. Knowing the endpoint is hard. And so we don't do as well on that as we do at just detecting the referendum. Okay, that gets that across. Okay, so here's, yes?
Well, I don't understand why repetition rate can be as low as 80%. Is it that it's getting false positives, or is it?
Yeah, so for example, that sometimes is a disfluency and sometimes is not a disfluency, right?
Really that frequent?
Well, yeah. Yes. Yes.
This is all on transcripts, right? Not on ASR.
This is all on transcripts. So all of those numbers would go down on ASR.
Still surprised that it's 80%. Wow.
And you can see it's even lower in call home. The more informal stuff is, but you can hear the difference if you use the audio. So if I had the audio, I think this would be much higher. If I had the audio and did a good job with extracting the prosodic cues, which is another thing. All right. Okay. So this is new stuff that we've been doing. We're unediting the SCOTUS transcripts. So the question was asked earlier about transcriptions, what people transcribe by LDC. When they're doing a careful transcript, they would get everything the person said. When you look at what they transcribed in SCOTUS, sometimes they would get the repetitions. They may leave out sometimes they'll put in commas to indicate there's something going on. They will put in ... when they'll do that for repetitions. They'll do that for those sorts of things. So there are no ums and uhs anywhere in this 50 years, or in at least the 20 years that I've looked at of SCOTUS transcripts. So the question is, so the thing that's frustrating is we've got all of this data. We have 50 years worth of data, so I can look at, disfluencies across time, speakers across time. Roberts was a lawyer, and then he was a justice. We can look at the difference. Actually, we have. And I could do all these things if I could use all this data. So how can we get it when it's not there? Well, what we're going to try to do is, so when I gave this talk at Penn, and Mark Liberman told me I was doing unediting. So that's what I've now called it. This is only based on text. I've been talking to people about a couple of things we can do based on acoustics, which are very exciting, and hopefully I'll can come back in a couple months and tell you about them. So we're looking at orthographic cues, particularly punctuation. But what we did was automatically match the training data to this format. So we're adjusting the training data. We're learning, so we have we have parallel versions of some of the SCOTUS data. So we learn where you would insert things and take things away. So we adjust the switchboard data, we map to the SCOTUS data. We then can apply, so now we have all this data that's not transcribed, so we can do semi-supervised learning. The other thing that made a difference is explicitly modeling repetitions separately from repairs, because the mismatch between corpuses is different for those two. Okay, so here's what we got. We started out, if you just use switchboard, and this is just doing the referendum, this is not doing the correction, because that was really harder to deal with in terms of the mapping. So if you just do switchboard, finding the referendum, this is where we start with, the original switchboard, okay? If I add the SCOTUS data, the careful SCOTUS data, so it's mismatched, I'm then doing the dot, 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 blah, 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 I get 41. I go from 40 to, basically 40 to 41. If I transform the data to transform switchboard, using what I learned about the difference, it gets up to 58. Pretty nice. If I add self-training, that gives me a little bit more. And if I use this different representation of the two different disfluencies, I get up to 62.2. So this is a really nice big jump. The thing that kind of blows me away is that we're doing better now than we were with the SCOTUS data that was all careful in terms of, we're now at 62.2 versus 41.6. Part of what's going on, there's multiple reasons for that. One is I've got more SCOTUS data but you can see the self-training isn't giving me that much. So I need to kind of figure out what's going on to make this big difference. But there's also the other thing that you can see here is the thing that is the hardest in the original is the recall. So, if we detect something if I get if the is there, I can be pretty sure that I trust it. All right, but the recall is what we mostly improve.
I'm confused about the annotation level. So there's the unannotated, or there's the transcribed data that's not, and then there's the LDC careful, then there's the unedited, right? So this is being evaluated on unedited.
So what we did was we took the careful transcript. So the test data has the disfluency locations in the careful transcript aligned with the non-careful transcript. So I know where they are, even if they don't exist in the non-careful transcript.
Right. Wait, but is the careful one, is that what LDC provided, the 1 year, or is that what you guys provided?
It's both.
Okay. But the SCOTUS one, that's the 50 years of original stuff.
Right.
Okay.
Right. So we took the careful transcript, and that's been hand annotated for the disfluencies, aligned the thing because they have different words, obviously. Right. Do the alignment, transfer the annotation so we know where the referendum is, and that's what we use for the target.
Okay. And you're doing this only on the test data or in the training data?
On the test, you do the transfer on the test data. We also do the transfer on a separate small set of because we don't have a lot of this stuff annotated. Okay, small set of training data, which is where we learn what the mapping between them is, and then apply that mapping to all of switchboard.
All of switchboard.
Right. So the thing we're transforming is switchboard. So we're adding punctuation and taking away words from switchboard.
So you're making switchboard look like SCOTUS, not
right.
the way around.
Right.
But is this gain then? Does that mean that is the reason for the low original F score just because of mismatched annotation standards rather than sort of?
No, the original is based on the matching careful transcription, so it's not a mismatch in annotation standards. It's a.
The training and the test are completely comparable in terms of their how they annotate both transcribe and annotate the.
Right. So the transcription. Well, I mean, different people who did it at LDC did this, decades ago. So it's not the same people, but to the extent that you're following the guidelines, it's the same.
I don't quite understand still. The event that you're measuring, that those precision recalls are on, the task is
that find the words.
Fill, and you have to put in the original disfluency.
Yeah, you want to find the words that are in the referendum.
But you're not.
So each word counts.
You're not allowed to insert a disfluency at any point in text. Right?
So if you miss a word that's in a referendum, that's hurting your recall. If you get a word, if you say something's a disfluency when it's not, that's hurting your precision. And it's a word level measure. So if your disfluency has 3 words in it, then that counts for 3. So it's not a disfluency level number, it's a word level number.
So if a regular person to do this annotation, would he get 95, 100 for F1?
Probably not.
Probably
No,
not.
because we've got, there's disagreements. There's disagreements for sure.
So what is the disagreement? At which level we may disagree with each other?
You know, I don't know for the LDC data. So I don't know. I mean, it was done a long time ago. And I'm not sure there's a paper on it, so I don't know. I know that they went through a bunch of iterations on it, and I know that there was some discussions on simplifying it. So for the later, so there's 2 phases of LDC annotation. For the later phases, they dropped the recursive structure. Okay. All right, so that's that. So I want to, I've gone too long. I just want to give you a few data analysis things. This is looking, so this is with the caveat, these results, so the unediting just finished. You know, it's very recent stuff. So all of the SCOTUS stuff here, this is on 20 years worth of SCOTUS. This is based on, I should say, this one. Okay, so what we're doing, so we have much lower recall. It actually, I think at the time, the way we were, it was a slightly different version and we had higher precision. So we had precision at about 0.8, but much lower recall. So these numbers all need to be updated, but you can still see pretty interesting trends. So this is just showing disfluency rates. Each X is a, let's see, I think each X is a speaker. No, is a case or a conversation. So, no, it's a speaker, sorry. So basically what this shows, so these are filled pauses, the blue bottom is filled pauses, repetitions, and other disfluencies. So you can see speakers vary quite a lot in both corpora in terms of these, how disfluent they are. Okay, that's the main thing. So the other thing, if you look at it from this perspective, the intra-speaker variability compared to is huge. So this is going across speakers and this is within speakers. So the variability, so there's a huge amount of variability. So to try to understand what's going on, if you were working with Scalia versus O'Connor, you would get very different conclusions. So it's important that we have an understanding of variability, speaker variability, in order to make any comments about the effect. And so things that I talk about with, and that's why we have this, for the blank find stuff, we have the before and after and stuff like that. So main point is, it's tricky because it varies hugely.
And also the 3 types don't correlate at all.
Oh yes, thank you. That was the other very important thing. I cannot predict how disfluent somebody is going to be by just looking at their filled pauses. So filled pauses are easy to detect. Repetitions are fairly easy to detect. I would like to be able to predict how disfluent they're going to be from one of these. I can't. So that's it. Thank you. There's, so it's roughly log normal for a speaker. Cross-type prediction is difficult, and controlling for speaker is important. So just a couple fun things. So if you look at the stress effect, so blank fine has more repetitions and more filled pauses in the higher stress hearing. In the weak versus strong task for the Taros corpus that we are looking at, the negotiation problem-solving task, there's again higher repetition rates in the strong stance case. Okay, so more the higher stakes case. There's also higher filled pause rates, particularly for men. So the stakes seem to cause people to be more disfluent, as you might expect. Now, we tried looking at judges in cases with unanimous versus close votes. And for the close cases, we were thinking, okay, what's happening if they're close and you're on the losing side? The highly disfluent speakers are more disfluent. The less disfluent speakers are less disfluent. Don't know what to do about that, okay? But again, I have to revisit this with our new improved detection. Some highly disfluent cases have 9-0 votes. They're just being more informal. I don't know what it is.
Do you have enough data on Thomas? I thought he literally said only a few tenths.
You notice he wasn't on the list. Yes. No. Actually.
But this is a highly emotionally charged one, too.
Yes. So there is no thing, but in fact, did I have a thing about?
Yeah.
Thomas? Okay. Yeah.
I guess that's the only case he actually said anything on.
Yes. For this particular one, it's a great thing to analyze. But I don't have him in other studies because there's just not enough to normalize. But it's very interesting, the types of disfluencies that are in that case, because it tells you exactly what the hot buttons are. Okay, so this is the blank fine stuff. You can have the early hearing and the late hearing. So this is just giving you details on the differences. And where the interesting thing here, if you look at where the disfluencies are happening, they're mostly happening sentence initially at the content planning stage. So he's thinking more about what he's going to say for obvious reasons. Okay, this one I love. The repairs reflect the power dynamics. The hedging repairs are mostly used by lawyers, as I said. So here's some examples, changing I think that to I don't disagree with that, except to the extent that I think that. So this is a classic. Let's see. This is another one I love. So many to, or not maybe so many, but many. Politeness, the lawyers tend to be polite and the justices aren't. So I'm sorry is an interregnum for lawyers. The other thing we looked at, which is fascinating, is entrainment. So you do not see, this is Scalia, who's interesting because he's so disfluent. If you look at cases, these are different cases. If you look at the repetition rate of the case here versus the repetition rate of Scalia, so it's, there's no trend here. If you look at the lawyers versus so here's the repetition rate of the case and the repetition of the lawyers. As the case gets more disfluent, the lawyers get more disfluent. And if you look specifically at the case, the lawyers who come in the second half, so you get your first lawyer and your second lawyer, in the second half, normally they start out very not disfluent because they're totally prepared. The second lawyer starts out disfluent, almost at the rate of the case.
Is this excluding the lawyer in question itself?
What?
Is the on the left-hand side graph, because if the lawyer talks a lot, then can't the
Right. So if the and so Scalia can be driving. So what's happening to some extent is if he's talking a lot, he's driving because they're patterning. The lawyers are patterning after the judges.
It would also be interesting to see the trend, A in-trains with B or B in-trains. So it's a lawyer who would going to in-train with the judges because of this power dynamics.
That's what this is showing. That the lawyer is in training with. So they're not. It's not necessarily. I haven't done anything with specific justices. But I have. But and remember, this has the problem that I don't have enough data yet to normalize for. I can normalize for the justices, but not for the lawyers, right? So really, it's just broad statistics that we can look at this point. But what you can see, because lots of people are arguing, and there's not a ton of time to entrain to one person. So it's the trend is overall to the case overall. That's all I've been able to do so far.
But it's also interesting to see locally. So who starts the disfluency first?
I don't think that we can do that without more speaker normalization. So yes, it would be really interesting, but I don't trust my data enough yet. Okay, so just some things: high engagement, more disfluencies, and we talked about some other stuff. Syntactic parallelism. One of the things. So there's this comment. This theory about the well-formed disfluencies having syntactic parallelism. The switchboard annotation that was done for parsing incorporates all of that and represents these unfinished constituents. And so one question is, what's going on in the data? And so we looked at so this is just a very small analysis. It's very anecdotal, but what you can see, so most of the work with parsing and disfluencies have been based on same phrase. Okay, so the same phrase happens a lot in switchboard. Almost half the syntactic parallelism, clear, simple syntactic parallelism happens a lot in switchboard. In SCOTUS, not nearly so much. No. Same syntactic construct. Okay. So what's different here is in SCOTUS, the higher stakes stuff where you have more strategy things, you have expansions because they're adding hedges or clarifying appropriateness stuff. You have a lot more function word differences. So one of the things that this doesn't account for, the syntactic parallelism, that's not parallel, right? That sort of stuff happens a lot, right? Because it's a lexical access thing. So those things happen, high cognitive load, lexical access, all this sort of stuff is happening more. So my point is just that the syntactic parallelism needs to be taken with a grain of salt. It's fundamentally there, but not always beautiful. The length of repairs, SCOTUS is longer. One of the things that's very interesting is that sometimes you have this quote unquote repair that happens. Let's see if I can. So you say something and the repair is like a whole sentence. Okay? So is that the practice in, and then they insert something, and then is that the general practice? Okay? So if you think about it as a repair, this whole entire thing is in fact a repair. That is a nightmare for automatic detection. So in fact, this is longer than it appears because I've collapsed all of the other disfluencies inside it.
So how many instances like this are there in the data, the end of the data?
In SCOTUS, A non-trivial amount. In Switchboard, not much.
So obviously your model isn't good enough to capture that.
We can't capture that. We can't capture it. And in fact, the annotators don't know what to do with it because sometimes there's like two sentences.
Does that impact the application? For example, think of the application of this kind of things, like either for understanding or for translation. For translation, you probably just translate this as is. And for understanding, probably if you talk about the content, probably to change the content much as well, including both.
So the reason why this is interesting, so for translation, it's probably who cares what you would want to do. What we were talking about earlier this morning is you might want to put in a ... where that plus is to let you know the person is, was thinking and something's going on. But for translation, I would say it's not a big deal. I think it's
won't break it into 3 separate sentences.
Yeah. The thing where this becomes interesting is if you're looking at any sort of social analysis, understanding what's going on, strategy analysis, then you want to know that there is something here. So it's more of a discourse level thing.
So like in Cortana, we just delete the whole thing.
Yeah.
Just get whatever.
Okay, so just to finish up, the implications here is, looking at a noisy channel model, it works really well for handling the easy types of disfluencies. So repetitions are frequent, so one of the things we've started doing is detect them first and deal with them. That's kind of useful for thinking about incremental processing. It works really well with incremental processing. Being influenced by Mark Johnson, PCFGs are not good for disfluencies. And the non-trivial number of long repairs suggests you need to have more sophisticated delayed decision making. Other implications, I think there's one of the reasons this stuff is interesting is if looking at analyzing social interactions and cognitive load. That's one of the reasons that I'm interested in detecting actually the corrections. So in conclusion, my main point is disfluencies are not just noise. They're interesting. They carry information. My second big point is we really need to be looking at this speech in the wild to see what people really do. And it is important for understanding the variability both within speaker and across speaker in order to handle disfluencies correctly and to improve our automatic detection. Speaker variability is huge, so that potentially impacts earlier findings. It also makes it hard to figure out social information and cognitive load information if you can't norm the speaker. Then with some context control, if you can do norming of the speaker, we can see pretty interesting effects of stress and power. So some of the things I'm doing for looking for or would like to do in the future is more on the semi-supervised cross-domain learning. I would love to leverage parsing. If I could get a parser to work on the SCOTUS data, I think it would be very interesting. I'm interested in ways to learn the finer grained disfluency categories, applying semantic analysis to them, and expanding the disfluency types for if we have these expanded disfluency types, can we use them for speaker modeling or analysis of cognitive and social factors? And lastly, we can apply this new way of looking at disfluencies in terms of multiple types as a way to improve parsing, to do a better job of integrating disfluencies and parsing. And that's it. So sorry for going so long.
So when they repair, like when you replace one word with another word, it seems like sometimes it's the type of thing where the words sounded similar, and they had just sort of said the wrong thing, and they were fixing what they said.
Right.
But I'm wondering, how often is it more that like the concepts are close, but they're totally different words, and so you kind of like you've changed your mind about how you wanted to express? Have you looked at the difference between those two things?
So I've tried to do some looking at that. These are less frequent. So of the The word repairs. So of the lexical access repairs, most of them involve function words.
Oh, right.
Okay, so I do have it, and you can, one of the things I've been trying to do is automatically mine the data to find those specific things. So we automatically mine them based on phonetic similarity, and also we tried to do some stuff where we looked at stemming and trying to find syntactic similarity. So we've done a little bit of mining the data for that. What we come up with hasn't been accurate enough to do fully automatically.
Because it's mostly function words, so you don't,
have a
lot of these types of...
Yeah, so a lot of it is function words. And the interesting, and I'm not sure, so I've talked about this with Ann Cutler, and she's the one that, told me that she thinks the function words are lexical access, a lot of the function word things. So like there's a lexical access thing. I don't know if that's a good example, but anyway, there's a bunch of function word things that are presumably lexical access issues. You'd have to do a much more controlled study than I can't tell. I've got the transcripts. I don't know what's in people's head. Sure. So I can't tell that stuff. I can just look at gross statistics.
So is the implication of this, rather than the type of downstream task that we usually think about, like translation, stuff like that, is it to actually get the disfluencies themselves so you can make analysis like this person is probably a subordinate if you have a conversation? Is that the kind of thing that...
So that is one thing that I'm interested in. So I'm actually interested in both types of things. So there's a couple reasons why it's relevant for translation. If you're going to throw something away, you may be throwing away something useful. So knowing the correction can tell you whether you're throwing away something useful. So that's one issue. The other issue is by working on all these different data sources, I've ended up improving my performance on switchboard. So it just gives us a better disfluency detector the more we understand the types of things people do. So it's relevant for that as well, but I'm just arguing that on top of that, it's relevant for understanding these social things.
No, I'm just wondering more about what are the applications in that space? Like, is it that type of thing like that I just exemplified before?
So understanding power relationships. Is this discussion, if you wanted to say, is this discussion going well? One of the things people are interested in is, analyzing how is this if you have recordings of a negotiation, how is it going? Those sorts of things.
But in translation, you could see, like, there's a power dynamic, it might play out differently in another language that you might want to capture that. That would be a difficult thing to do, but, like certain honorifics that might be expressed in a particular power situation that is clear from the disfluencies. I'm not saying that's something we'll do, but it's something you might want to do.
Yeah.
So as you mentioned, you do more disfluencies in a more informal environment, and you said, like, in this talk here, if this was a more general audience, you'd be speaking kind of more carefully. Do you think we sometimes use disfluencies as a way to signal to the audience, like, how we feel with them, or not just audience, but the other person we're talking to, more than just that it's subconscious, but it's...
I think it's mostly subconscious. I think some of the things that we do are going to be conscious, the really long ones.
Yeah, sorry, I misspoke. I didn't mean that it's not subconscious. I meant that it's not just like an accident that we're making disfluencies, but that we might be kind of trying to signal by not knowing that we're doing it, but that the signaling is there.
So there, it has been argued that we do purposely, that it's purposeful. I'm an engineer, so I'm not going to go out and I'm not a cognitive scientist, but I will say, you can. It is certainly the case that people use them. Whether they use them because we're intentional, or whether they use them because they've just gotten used to this sort of disfluencies mean X, I don't know. But definitely people use them. And so speakers and listeners both use them.
Do you know if there's been studies that have shown the effect on a listener if a person has different disfluency? So for instance, if we had like when the computer is talking to a person, if it injected disfluencies every once in a while, would that like have an effect of making the person feel more comfortable? Like, do you know if that kind of thing has been looked at?
So, I don't know if anybody's, you guys.
I think that is the case, for example.
That's the work you're doing, right?
Yeah.
That's mine.
Yeah.
My time will be tomorrow.
This is an advertisement for her talk.
She wanted me to ask that.
Okay. I see. Okay.
Do you think other incremental parsing techniques like TCG and other formalization would be better for handling long-range repair? Because you can get partial parsing rather than...
So I've talked to Mark Steedman a bit about this, because we were trying to, when I did my sabbatical in Australia and Mark was there with Mark, I was with Mark Johnson and Mark Steedman was visiting, and we spent a bit of time talking about CCGs, and his feeling is that CCGs, and we actually did a little bit of analysis, that CCGs do a better job at meeting this syntactic parallelism, well-formatus theory. Okay, so that there are the constituents that you see people use are more compatible with CCG. And that was the hypothesis. It mostly seemed to be bearing out, but it didn't, we didn't actually really write anything up. It was just kind of anecdotal, trying to figure out what to do. We were looking at it because of my hypothesis about the repetition, handling the repetitions. So, I think it's an interesting direction. We looked at it a little bit, but, definitely no complete study.
Another question about prosody. So what we are missing to get something out of prosody? Is it only the alignment with the speech, or the lexical feature are getting us enough improvement?
So if you look at work that's been done on Switchboard, you get most of the bang for the buck from lexical features. A reason for that is because a vast number of these disfluencies are repetitions in Switchboard, right? And that's going to dominate your detection measure. So if we look at more complex disfluencies, I think it's potentially the case that prosody could give us a bigger win. The problem is that with these corpora, these more interesting corpora, most of them, with the exception of Ataros, which is recent, the SCOTUS and the FCIC data quality is not good. And so I've tried doing forced alignments on them with multiple aligners, and it's just not good enough. I mean, it's stupid things like, it's a robust recognition. We should do the deep learning on it. It's just stupid things like page turning totally messes up the forced alignment.
Yeah, so the earlier model you talk about, like cognitive model for planning and articulation misalignment, that looks a very, very reasonable model, a hierarchical model. So do any people make any computational models based upon that kind of hierarchy, the causal relationship between the two, in order to explain, the kind of difference you have to help with?
So there's not, there is not computational work doing that I am aware of. So this was my sabbatical in talking to cognitive scientists. So there's not a lot of computational work.
So in your transcripts, you have several things that aren't actually going to come out of an ASR system. You have ellipses, you have commas, capitalization. To what degree did you use those things in the systems that you built? And did they help you?
So I use those for the SCOTUS transcripts for only doing lexical things. What I would do in hindsight now is I would use those in forced alignment to look for filled pauses. So if I did forced alignment with an optional insertion of things and optional, so one of the things, I've done some work actually that Lucy knows about on taking oral readings and looking at where people make mistakes to try to understand reading level and difficulties, and that the forced alignments were done by somebody who automatically inserts, has a way of inserting words, allows it to insert words, so you could allow it to learn repetitions and things like that, to find repetitions. So if I did the forced alignment that way, I could use the ... and punctuation to up the probability of those sorts of things. So that's one thing that I would like to do next.
When you say repetition, like typically you talk about the, is repetition an exact lexical match or is it a functional match? So you're talking about the. In another language you have ella, didas, das. Okay?
So I'm using it to mean exact match with exact lexical match with the caveat that I include. So if I had the example a requirement. All of that is trying to get out that final a requirement. So a rec, I'm counting even though it's just a fragment. But you can call that a match by doing a substring.
But that's considered a repetition.
I am considering, that's by my definition, that is a repetition.
Whereas this der die case would be a case of lexical access, because as you are planning and you are coming up with, I'm going to say a different noun, now I have to modify, that would be a lexical access.
That would be a lexical access one, and that would be count. So there's the surface form, and then there's these more interesting categories. So the surface form is just, are they the exact same string or not? That's, that's repetition, repair, restart. So these other categories are things that I'm starting to work on, where trying to use sources that will say, is this syntactically the same? Is this semantically the same? So the part of speech match, der, die, and those things you can get with a part of speech match. They are thought to be associated with a different level than the repetition.
We should break here. Thank you.
Okay, thanks.